Hi everyone! In this video, I'm going to go over some of the multiple choice questions from my lecture notes. We'll start with the questions from Chapter 19 on celestial distances. This question asks, imagine that you are viewing a star that has an apparent magnitude of 0.2 and is located about 100 parsecs away from us. Which of the following is most likely the star's absolute magnitude? Remember, absolute magnitude is the magnitude the star would have at 10 parsecs. This star is a lot farther away than 10 parsecs. It's at 100 parsecs. That means that the star would look brighter if we saw it from 10 parsecs away. We need to choose a magnitude a lot brighter than 0.2. This means a smaller number. The only choice that works is minus 4.8, or answer A. This question is asking about a star that has a parallax of 0.1 arcseconds. What is its distance? Well, distance is given by 1 over the parallax angle. So here distance is just 1 over 0.1 arcseconds, or 10 parsecs. The answer is A. This question is very similar to the previous one. A star has a parallax of 0.01 arcseconds, so what's its distance? Again, distance is 1 over the parallax angle, which here is 0.01 arcseconds. 1 over 0.01 is 100 parsecs. So again, the answer is A. This isn't a question from the lecture, but I wanted to do an example using the distance modulus because you'll need to use this equation in the lab. So this question asks, the star Sirius has an apparent magnitude of minus 1.45 and a distance of 2.64 parsecs. What is the absolute magnitude of Sirius? The question gives us apparent magnitude and distance. We want to know absolute magnitude, and we can get this from the distance modulus, which tells us that the apparent magnitude minus the absolute magnitude is equal to 5 times the log of the distance minus 5. We need to rearrange this equation to get the absolute magnitude. You can do this in any way that works for you, but here I end up with the absolute magnitude being equal to the apparent magnitude minus 5 times the log of the distance plus 5. If I put in the numbers given in this problem, I have m equals minus 1.45 minus 5 times the log of 2.64 plus 5. After putting all that in a calculator, I get an absolute magnitude of 1.44. Here is another distance modulus example. The star Capella has an apparent magnitude of 0.05 and an absolute magnitude of minus 0.54. What is the distance to Capella? Again, look at what you're given. We have the apparent and the absolute magnitude. We need to rearrange the distance modulus to get at D. Now, I've done this for you here, and it's also done for you on the lab. So when you get to the part on the lab where you have to calculate distance, the equation is already there for you. And here's how it works. Distance is 10 raised to apparent magnitude minus absolute magnitude plus 5 over 5. Note that the 10 is raised to this, it's not multiplied by it. So now let's put in the numbers. I think it's easier to do everything that 10 is raised to first. So we have 0.05 minus negative 0.54 plus 5, and then all of that over 5. So I get 1.12 for this. Now what you want to do is raise 10 to 1.12. don't multiply. It's 10 to the power of 1.12. If you put this in your calculator, you should get 13.2 parsecs. Now let's look at some questions from chapter 21, mostly about the discovery of planets outside of our solar system. This is a question about the Doppler shift method for planet detection. It asks, from the observer's perspective, when the star is at position 1, absorption lines in the star spectra are blank. I'm going to offer a general hint for all of these sorts of questions. We are always looking at the star, not the planet. We need to figure out what the star is doing when it's at position 1. Now, perhaps you've already figured this one out, but if not, let's look more closely at what's happening. In these situations, the star and the planet are always in orbit around one another. Note also that they are always moving in opposite directions. When the planet is moving towards us, the star is moving away, and vice versa. We only care what the star is doing because we're looking at the star spectral lines. For example, in this snapshot of the motion, the planet is moving away from the observer and the star is moving toward the observer. Here, the star spectral lines are blue shifted. A little later, the star and the planet have moved, and here both the planet and the star are moving perpendicular to the observer's line of sight. The star is not moving toward, it is not moving away from the observer. In this case, the observer sees no shift in the star's spectral lines. And a little after this, the star and planet have moved so that the planet is moving toward the observer and the star is moving away. If the star is moving away from the observer, then the spectral lines are red shifted. Coming back to our original question, what is the star doing at position 1? At this point, it's going to begin moving towards the observer. The lines will therefore be blue shifted. This question has to do with the transit method for planet detection. It's asking, a transit of an exoplanet is shown below. Which labeled time interval corresponds to the diameter of the planet? And we're given a light curve and several options. So let's look more closely at what's going on with the light curve. When the planet and the star are separated, we get the maximum amount of light for the system. And we'll observe the same amount of light until the transit begins. Once the transit begins, the planet starts to block light from the star and the light curve dips. When the planet is fully in front of the star and transiting, the light curve is at minimum brightness. It's not changing as the planet transits. It's a straight horizontal line. The diameter of the planet can be found from timing how long it took the system to go from maximum brightness to minimum brightness. The time period here gives us the diameter of the planet. The time it takes to go from when the edge of the planet first crosses the star until that edge makes it completely across the star will give you the diameter of that star. On the other side of the transit, we can again get at the diameter of the planet. Looking again at this question, you should be able to see that option A is the choice that gives you the diameter of the planet. Okay, last question. The Kepler Space Telescope is searching for exoplanets by the transit method. It is necessary for Kepler to monitor a large number of stars because choice A, says that only a small percentage of systems are likely to have planets. Well, this is false. Our understanding of star formation shows that planets are likely to form around stars when those stars form. Choice B says that only a small percentage of systems have the correct geometry for transits to be observed. This is true. We need the systems to be edge-on to see a transit. Choice C says that planets will only be transiting the star for a small percentage of the time. This is also true. We only see the transit when the planet is crossing the star. Therefore, the correct answer here is choice E, both B and C. Okay, I hope that helped with the lecture questions. As always, take care, and I'll talk to you again soon.